Now we will see the waveform of the input current. This is I is the input current. So the current from the input will be drawn during the both positive half cycle and the negative half cycle. So this is during the positive half cycle from alpha to pi, in which IT1 and ID2 are conducting, and this is the waveform during the negative half cycle, in which IT2, the second thyristor, and D1 were operating. This is my output load current, which is available throughout the time, and this is IDM. This is the current from the freewheeling diode from duration 0 to alpha, in which none of the thyristors or diodes were operating. The freewheeling diode was conducting. The previously stored energy in the inductor was freewheel into this circuit load, and we were able to obtain an output current equal to IA. And then during this interval, which is from alpha to pi, the thyristors were operated, and this freewheeling diode, it came into reverse bias condition, and the current IA was provided by that pair, that was IT1 and ID2. They were providing current during this time, and then once again when none of the thyristor or diodes were operating from pi to pi plus alpha, this freewheeling diode was again conducting, and when once again the second thyristor was triggered, in that case this freewheeling diode will go into reverse bias condition, and this one will be the second pair will be providing current to the output. The average output value can be found from this formula. VDC is equal to 2 over 2 pi alpha to pi Vm sine of omega t d omega t. This multiplied by 2 is due to the even wave symmetry, divided by its complete time period, and we know that it was conducting from alpha to pi. So and this is the quantity V input. V is equal to Vm sin omega t. This was integrated, so we get this expression 2 Vm or 2 pi multiplied by minus cos of omega t, and limits are from alpha to pi. The net value, the net expression is Vm over pi 1 plus cos alpha. So VDC can be varied from 2 Vm by pi to 0 by varying alpha from 0 to pi. At cos pi, at alpha is equal to pi, cos alpha is equal to minus 1, this expression will be 0. Basically it means that we are not triggering the thyristor during the time period 0 to alpha. So how can I achieve any output voltage at output? And if it is triggered at 0, in that case cos alpha is equal to 1, and I will get 2 Vm by pi. Now we have to calculate the RMS output voltage. It can be calculated by taking the square of this expression V is equal to Vm sin omega t, solving this whole integral, and then taking its square root. Hence root means square value. So from this step we move towards this step, and in terms of alpha, this is our final expression for the RMS value of the output voltage. So if we know the value of alpha, we can put over here and we can get the corresponding RMS value. and correspondingly once we have determined the value of this RMS value, we can calculate the output current as well. I naught RMS is equal to V naught RMS, our resistance.